In the fourth video for SLO7, we'll be looking at a permutation of a reaction we've seen in previous videos. We'll be looking at the additions of amine nucleophiles to aldehydes and ketones. So in this case, I'm showing an aldehyde. And so what we'll look at here specifically is a reaction that seems a little bit analogous to acetal formation in the sense that we'll catalyze this reaction with an acid, but we're actually going to use a weak acid here. So you might run the reaction in acetic acid as a co-solvent, or maybe you use a buffered solution with a pH of like 4 or 5. So we could write something like a weak acid catalyst. Need to make my reaction arrow longer here. And so when we do this reaction, something a little bit interesting happens. Rather than just a nucleophilic addition where the nucleophilic nitrogen adds to the electrophilic carbonyl carbon, we actually form two new carbon nitrogen bonds into what will look like a new functional group to you, but is very important both from a pharmaceutical chemistry perspective as well as a biochemical perspective. This is called an imine, I-M-I-N-E, where we're noting the difference in the number of carbon-nitrogen bonds, so like a double bond versus a single bond, with an A versus an I. So this is also distinct from a nitrile, which has a carbon-nitrogen triple bond. Okay, so this imine formation, it looks in some ways very unique. I mean, we're making a carbon-nitrogen pi bond. We've probably never done that before in any reactions you've learned this year. But in some ways, it looks kind of like acetal formation. I have an acid catalyst. It looks like I'm forming two bonds to the electrophilic site. That sounds like acetal formation, right? Two new CO bonds in those cases. And I think the best way to make sense of what's going on here is actually to work through the mechanism of imine formation. So we'll do this with the same structures that we started the video out with. I am going to abbreviate the benzene ring pH just to save space. And so we can start to think about some roles and likely interactions that happen initially here. So nitrogen lone pairs are not that highly stabilized. We learned about these as being somewhat basic. You know, they're the conjugate acid pKa's for these are ammonium ions, so around 10. So really, this is a fairly good nucleophile, and it turns out there's really not a need for a catalyst for this initial kind of encounter. So this is a little bit unusual. Normally we say things like, well, protonate something first in an acid-catalyzed reaction, and that's fine. You can write a mechanism that way. But I guess my view is that it's not even necessary. And so we get to a structure that looks like what we'd expect from any kind of a reversible nucleophilic addition. We form a new bond to the electrophilic site, and we're going to end up with an O-. Our nitrogen is neutral, but it's forming a bond with its lone pair, and it's not losing either of its protons in this step, so the nitrogen becomes positively charged. The rest of the aldehyde is a spectator, and so we end up with a structure that looks like this. So if we get to this addition step, we know that one possibility is just to eliminate this nitrogen group back out, and that happens. But the other thing that's possible is for there to be a proton transfer between the O-, which is highly basic, and this somewhat acidic ammonium ion now. So we could imagine also forming a neutral version of our product that looks like this. So we've got an OH group, we've got an amine attached to the same carbon. This is probably reminding you a little bit of like acetals and hemiacetals. This compound actually has a pretty fun name, or this kind of structure where we have an amine and an alcohol that are sharing a carbon. We call these hemi. There's that idea again of half of some other functional group. Am for amine, and now al for aldehyde. So hemiaminal, or if you feel like being cheeky, you could call it hemianimal, which a lot of people do accidentally. So this functional group tends not to be particularly persistent. So a lot of times if I make this, the reaction will start to run backwards, because this position here so far is a position of maximum stabilization. Here's where the acid catalyst comes in now. So imagine we have a proton that's now floating around. Again, we won't specify the structure of the catalyst because you could use a lot of different types of things. And now I have to think about, well, where in this molecule that I'm proposing, this hemiaminal, could I actually add a proton? I'm looking for basic sites. Well, one option is the nitrogen lone pair, and that's probably the most basic site in the molecule, but that basically is going to start sending you back down this path. Instead, we could think about protonating the oxygen, because if I look at the structure of what I'm making eventually an imine, it looks like that CO bond needs to go away. I'm going to break it, but right now there's no good way for me to do that. So this acid catalysis is really about making this alcohol into a better leaving group, which we've seen many times this semester, including in the previous video. So this acid-base step may not be particularly favorable, but it's important for this mechanism. So we end up with a protonated alcohol, which is now an excellent leaving group. And so that, well, it'll leave to form a carbocation. But again, normally we don't invoke carbocations unless we absolutely have to, or there's something about the carbocation that's unusually stabilizing. So like, a secondary carbocation, not a good plan. But if I could identify like electron donating groups, then maybe that carbocation is more stable. And then I could expect it would form more quickly. So if I draw the structure of the carbocation, maybe I can find some visual cue to identify why this carbocation would form more readily than others. And if I draw the structure, one of the things I notice right away is that this nitrogen lone pair is going to be an excellent resonance donor to stabilize the positive charge. In the same way we thought nitrogen groups as good resonance donors to carbonyls. So really what I can do is think about a resonance structure where I have a new carbon, nitrogen, pi bond, and the lone pair of nitrogen is gone, and I have a positive charge on nitrogen. This looks a lot like an imine already, though. If I look at this structure and this structure, interesting. So this looks like a protonated imine. And all that's left for me to do now is to turn the catalyst over. So I'm going to dissociate the proton off. Ooh, hello, pen. Which is good. If this is acid catalyzed, I need to form a proton at the end of the reaction here. Okay, so this is our mechanism for imine formation. It looks very much like acetal formation in the sense that there's an unfavorable nucleophilic addition to form a structure like so. There's an intramolecular proton transfer, followed by catalysis to make a good leaving group, where I can form a carbocation that's resonance stabilized. And then finally, in the acetal formation, we would add another equivalent of nucleophile. In the imine formation, all we're doing is rationalizing the formation of this second CN bond, which comes about from the donation of electron density on nitrogen to the carbon. So this is very similar, but not the same as acetal formation. So in the last section of this video, we'll actually look at a few reactions where we're making imines, as well as what we're going to call imine hydrolysis. Because as you can see, all of the steps that I've drawn here are reversible. And so you could imagine that you could push these types of reactions like one way or the other, depending on how you run them. So let's look at some examples where we actually make imines first, and we can do this from either aldehydes or ketones. So in the previous section of the video, we looked at an example where we made an imine from an aldehyde. To get started, we'll then look at a case where we make them from a ketone. And so just keeping with the theme of using cyclohexanone, because, well, everyone loves hexagons, we can look at this reaction and we'll pick a different kind of an amine, one that's got a little bit of structural interest in it, something that's not just a methyl group, for instance. And so I want to think about what will form in this case with a weak acid catalyst. So I'm going to start by identifying electrophilic sites and nucleophilic sites. Carbonyl, carbon is going to be my electrophilic site, and nitrogen here will be my nucleophilic site. And so what I'm noticing is carbonyl plus amine, especially in the case of an acid catalyst, I might think about connecting those, but then actually forming two bonds between them. which we know mechanistically why happens, but isn't always convenient to go through that whole process every time we want to draw the structure of product. So I'm going to start by making sure I connect my electrophilic site to my nucleophilic site. So I'll add my labels to the product just to make sure I've done that. And then I'm going to think about what else is going on here. Well, I've got this whole 3-carbon chain on the nitrogen still. That's not involved at all. So I've got a little flag, I guess. And I know that I'm going to form another bond between the nitrogen and the carbon. So there should be 2 bonds between what we're describing as our nucleophilic site and our electrophilic site. The last thing I want to remember is that this oxygen is going away. I'm making water as one of my side products. Remember, I protonate that alcohol to make it a good leaving group. Well, it leaves as water. And so the other product here will be H2O. Both of the H's and the amine end up in that side product as well. So really, what we would not care about the water typically, as we talked about in the acetal video. We would be trying to remove the water as it forms to drive this reaction forward by Le Chatelier's principle. And so you could draw it or not for the product. Really, what we care about is the imine itself. So let's look at another example. We'll go back to aldehydes now. So we could use an aldehyde like so. And let's use an amine. With an alcohol group attached just for some fun. And our catalyst. So I'm going to play the same game. Electrophilic sites and nucleophilic sites, but now I have choices to make. I know from the pattern and the fact that this is a video on imines that the nitrogen might be the more nucleophilic site, but I should be able to justify that from structural arguments also. So if I think about the lone pair on nitrogen, it's less stable than the lone pairs on oxygen. Oxygen is more electronegative. That means it's a better home for electrons, and there's less of a driving force for oxygen to actually act like a nucleophile. So if I have multiple nucleophilic sites in a compound, I'm going to pick the most nucleophilic site to get started, and that's appropriate here too, where I could think about this nitrogen adding to the carbonyl carbon of the aldehyde. So just like before, I know that only a small part of the structure is going to change, and I'll use my labels to make sure that I make the right kinds of connections. So the carbonyl carbon is still attached to an isopropyl group and a hydrogen, and then I know that I'm going to form a new bond to what I'm deciding is my most nucleophilic site, the nitrogen, and that this nitrogen is going to be attached to all this junk that it's already attached to, but not the hydrogens on the end. So I have a structure that looks like that, and the last thing for me to do is think about how many carbon-nitrogen bonds are forming. I see that this pattern is typically that there are 2. So I've got a carbon-nitrogen bond like so. And water is still going to be my side product, which I will write for completeness sake, but remember, you don't have to. I'm not going to be worried if water doesn't show up in a box. Okay, so we've got a couple of examples of imine formation. You can see the pattern, but I also want to show you how we might execute the reverse reaction. So we could talk about imine hydrolysis, which is probably exactly what it sounds like. We're going to use water to break apart an imine group. So if I thought about having an imine that looked like this, I would want to hydrolyze it, which means I probably need to be using some water. And what we're doing is the reverse of the imine formation. We're running the whole reaction backwards. We know that if we're trying to run the reaction backwards and the forward reaction involved the catalyst, we're going to need to use a catalyst to make this go backwards. So we'll use a weak acid catalyst here too. And what I want to think about then is essentially looking at these imines and going the other direction. So that means that I'm going to break apart both of the carbon-nitrogen bonds and replace them with an oxygen. I can do this using the same kinds of roles. So the imine carbon is still electrophilic, right? We have a polarized bond. The nitrogens are moving electron density from the carbon, both by resonance and induction. And our oxygen here is relatively nucleophilic. I mean, not super nucleophilic, but it has that role. It has some lone pairs. And so I would connect my nucleophilic atom to my electrophilic atom. and that would make a new carbon-oxygen bond. But as this compound unravels, we end up going all the way back to a carbonyl. So in this case, the benzene ring and the H will still be there. All I'm doing is replacing the nitrogen for an oxygen. And this whole unit, the nitrogen and whatever non-hydrogen groups are attached to it, those are intact. So I'll still have a nitrogen with an ethyl group. And then the 2 protons from water end up as part of the amine. So what we're seeing, excuse me, is the direct reverse. If I had written these structures on the left-hand side of the arrow, you would have predicted the structure forming. Remember that these hydrolysis reactions, they're literally the exact reverse of how you would make the functional group. So if you make imines like this, then the hydrolysis would be the exact opposite.